Okay, welcome everyone to our Transportation CANS seminar series, and I believe this is the second CANS seminar of the semester. And what we would like to do, you probably heard last week as well, what we would like to do is that we have a series of student presenters going over the TRB paper presentations repeated here. And we will be alternating, I guess, then speaker presentations with those with the invited speakers. We have also several good lineup of invited speakers for this semester. So we will be alternating invited speakers with student presentations. And the way that we get basically two presentations from the TRB papers in one CANS seminar, so we will be able to cover a good number of those throughout the semester. For the first TRB paper presentations today, we have two of the papers actually as ICT projects. These are having the same TRP chair. Again, this is Sheila Shears is the TRP chair from IDOT Bureau of Materials and Physical Research, and they're very much closely linked topics on aggregate materials. So the first paper will be presented by Hasan Kazmee, who's been around for 3 to 4 years now, and 5 years. Well, years fly when you're having fun, right? So at least for 3 years he's been working on this project, I know, which we started, the 124 project. And this has the focus of the aggregate subgrade, basically, tried out in the full-scale experiments that we are running. So he will talk about the performance investigation of these non-traditional so-called aggregates, because they're large size as well as some recycled materials plus virgin materials. And then his presentation will be followed up another TRB paper by Vincent and Wentig next. So with that, Hasan, 20 minutes each. Right?
Thank you, Professor Chitumgar. Welcome to our CANS seminar. Today's topic will be performance investigation of non-traditional aggregates used as remedial measures for weak subgrade. It's a part of the ICT R27-124 research project, and I would like to acknowledge at first the TFP chair, Sheila Shears, for funding and sponsoring this project. So next we'll go up for the presentation outline. First, we will present some background information. Then we will show you what are the materials that we have selected for this study for performance specification of aggregate subgrade materials. Then we will go for the test section layout that had been proposed for the construction of the test sections that were built for this project. And how did we modify the subgrade strength to match a certain subgrade strength like CBR3 or CBR1, what was done. We'll explain that as well, followed by construction and quality control. Then we'll present the test results, some of the test results from the accelerated pavement testing and associated pavement forensics like dynamic cone penetration testing, variable energy panda penetration testing, or ground penetrating radar, or even the actual test section trenching images. And finally, we'll just summarize the research progress from this project. Research objectives. The primary objective of this study is to development of characterization technique for aggregate subgrade materials in terms of source, composition, particle size, and shape properties. That means IDOT uses the different districts of IDOT uses different types of aggregate subgrade materials or sub-base materials for weak subgrade stabilizations. And a majority of those aggregate materials, we don't know how the materials will behave in the field. And some of the materials are so large, like 6 to 8 inches of top sizes. So sometimes conventional laboratory testing is not enough to characterize the properties of those materials. So that's why we were kind of shooting for evaluation of field performances. How do we do that? We construct the test sections with those materials and basically do accelerated pavement testing And for this, we have built 12 different combinations of unsurfaced working platform or construction platform and 12 different combinations of asphalt surface low volume pavements. And according to those results, we'll then revise and develop material specifications governing the use of these materials. So this is the current IDOT specifications for crushed stones, or what they are calling it right now, aggregate subgrade materials. As I have said earlier, that some of the aggregates are really large size, some of them are very uniform like railroad ballast size. And finally, we came up with 6 different types of aggregates for aggregate subgrade material and 2 different types of materials for capping material. The 6 different types was named as type A, B, C, D, and E. A was the railroad ballast size materials, that is called RRO1 gradation. Type B is large size crushed concrete, rubberized concrete that is opted to fit in the CS01 gradation band prescribed by IDOT. Type C is basically primary crusher run. Most of them are in the size range of 4 to 6 inches. Some of them are even as large as 8 inches. Then we have 60-40 blend of large recycled concrete and recycled asphalt pavement materials. That was also expected to fit in the gradation of CS01. And then type E is the coarse fractionated wrap with very limited amount of fines, even less than 1%. Type F is the large size base coarse aggregate, CaO2. It's basically very similar to CA6 materials with a larger top size. By larger top size, I mean 2.5 inch. And finally, type G is the capping material. That's the typical Illinois base coarse aggregates. That's a dolomitic material and fits in the CA6 gradation band. And these are the final field gradations that we have got from the Sieve Analysis. As you can see, some of them are very large size. These 2 materials, type A and C, the primary crusher run one and the rubberized concrete, those are primary crusher run, and the RRO1 type A material is very uniformly graded. These 2 are recycled materials. Type B is the crushed concrete and type D is the 60-40 blend. These are somewhat well graded, but type D doesn't fit in the CS01 gradation band that we were expecting. Type G and E are comparatively very well graded. Type G had almost 10% of fines. And finally, type F is the CaO2. That's almost similar to CA6 materials, just a larger top size. Here we have got the top size as 2.5 inch. Oops. Yeah. So we have divided the whole test strip in 3 different cells, cell 1, 2, and 3, and each of the test cells have 8 different combinations of pavements. On the north side, we have 4 different combinations of construction platform. On the south side, we have 4 different combinations of HMA pavements. So 24 different pavement combinations. And this was the proposed thickness layout. For the subgrade strength of CBR1, we had almost 3 inches, that means 7.6 centimeter of capping materials, and beneath that we had 21 inches or 53 centimeter of aggregate subgrade materials. For cell 1 and cell 2, we have built those aggregate subgrade with type A, B, C, and D materials. And for cell 3, we had another 4 sections that were built with 2 different types of aggregate subgrade materials that were type E, the coarse fractionated wrap, and type F, large top size CaO2 gradation, CaO2 aggregates. And on the south side, we had an additional 3 inches or additional 7.6 centimeter of capping. That is total of 15.2 centimeter or 6 inches of capping in total. And on top of that, we had 4 inches of HMA. Because of the time limitations, my discussion will only be limited with the cell 3 construction platform performance evaluation. These were the overall layout of the Atlas test setup. While when we have placed on top of one cell of materials, it can cover up to 4 sections on one side. So what I will be discussing will be construction platform, that means CP, CP 9, 10, 11 and 12, these 4 sections. Before going to the field, we have already established what sort of moisture density relationships the soil is exhibiting, and for that corresponding density and moisture content, what was our strength level in terms of CBR. So that was established already. Like for CBR 3, the dry density was 120 PCF pound per cubic feet, and the moisture content was 13.6. Similarly, for CBR 1, what was the target moisture content? It was 15%, I guess. So we went out to the field, we scrapped the materials, we tilled the materials to a depth of 12 inches, and then we collected the moisture, we collected the soil samples and identified the moisture amount with the microwave, and we were trying to plot the moisture profile all over the test strip, like for cell 1 or cell 3, whatever we were targeting. And after plotting the moisture contents over that longitudinal and transverse distance, we were identifying the zones of moisture deficiency. So how much moisture is needed. So from that artwork, from the volume of artwork, we were calculating how much water is needed, and according to that water content, we have further added moisture, and then we went back and then again did the dynamic cone penetration test, and through the dynamic cone penetration test, we were matching the required CBR level. These are some of the pictures of the construction and quality control that we have done. Once the subgrade strength was matched, we sealed the subgrade with an asphalt coating so that there is no moisture escape. On top of that, the aggregate subgrade materials were placed. In the meantime, we tried to maintain a grade since the compaction of this type of aggregate subgrade materials, which are very large size, sometimes it becomes very difficult. So that's why we tried to maintain the grade using a laser guided grade control. Also, on top of the aggregate subgrade materials, we have placed aluminum foils so that we can track subsurface deformations or subsurface rotting if it was happening with the ground penetrating radar. We have also used nuclear density gauge to check the density, also used lightweight deflectometer and geogauge for the in situ stiffness parameters, as well as once we have constructed the pavements, this was the finished tapping surface and the finished HMS surface, with increment of rotting progression during the accelerated pavement testing. We have also done the ground penetrating radar scanning. This was the nuclear gauge density. Sorry for the section 17, 18 and 19, 20. These are basically section 17 refers to CP9, 18 refers to CP10, and 19 refers to CP11, and there goes on. So in cell 3, all of the for the aggregate subgrade materials, type E and type F showed very similar level of compaction, and the dashed line that you can see is actually the laboratory compaction characteristics that were earlier established in the lab with a standard compactive effort. Compared to this line, we can see that type E, both type E and F has shown comparatively lower densities, lower achieved densities. Similarly, we have traced the nuclear gauge densities on the capping layers. All of these densities were checked with backscattered method for the limited thickness. And as you can see, compared to the type G laboratory maximum dry density, it was quite lower. but throughout that section, we have seen that throughout that cell, we have seen that both type G and type E showed very similar level of compaction. These were the surface moduli from the LW lightweight deflectometer testing. We just used the Boussinesq's half-space equation that they prescribed to come up with these surface moduli. As expected, with inclusion of every layer, there was a general trend that the surface moduli was increasing, and also compared to the virgin aggregates, type E aggregates, that's the RAP was exhibiting higher moduli. That was also validated through previous literature studies. Then we have also done the strength assessment with dynamic cone penetration testing as well as PANDA penetrometer. PANDA is basically a variable energy penetration testing. Along with that PANDA penetration testing, we did geoendoscopy. It's basically you do the PANDA penetration testing, you take out that cone, and through that same borehole, you best shove a endoscopic camera, small endoscopic camera, to see what sort of things going around beneath the surface. This is the rotting accumulation in section CP9, construction platform number 9. And as you can see that it showed quite good performance. It survived actually up to 1,000 passes. And it was built on severe 3 subgrade with a type G capping, that means with a dolomitic capping. And after trenching, this was the thing that this was the overall profile that we have got. Mostly failure in the aggregate layers, as well as the subgrade was affected to some extent. Somewhat lower number of passes, it's section CP9 that was built with a wrap capping on top of wrap. That means we supposed to have 12 inches of wrap materials, and we basically did the accelerated pavement testing on that, and it survived only 250 passes. Also, aggregate is failing within its own structure. Also, some of the deformation is transferring to the subgrade. And this is the PANDA penetration testing and the dynamic cone penetration testing. On the right side, you will see that cone penetration, dynamic cone penetration testing results. On the left hand side, you will see the PANDA penetration testing. As you can see that below that aggregate subgrade, there is a depth of 12 inch of engineered subgrade, and somehow section CP9 and CP10 ended up with a higher severe values, and that has contributed to significantly improved performances compared to the other 2 sections. These are the ground penetrating radar scanning. As you can see, after 200, this was done after 200 passes, and after 200 passes, section CP9 virtually showed no sign of deformation compared to the other sections. These 2 sections, section CP 11 and 12, has already failed. This has survived up to 200 passes, and as you can see on this one, this has failed earlier. And one thing I need to mention, that is the wrap cap sections, that means section 18, section 10 and 12 showed higher magnitude of deformation compared to the CA6 dolomitic capping layers on the other 2 sections. This section failed, section CP11 failed at 150 passes. This was the overall profile that we have got, and this was section 12 test results. And compared to the other sections, you can see that there was a lot of thickness variation that has been going on. And if you look at these sections, you will see that the target CBR values were right on the CBR3 line over here compared to the wrap cap sections. So that's why these sections actually perform less than the other two sections. So higher thickness of wrap aggregate subgrade layer contributed to somewhat better performance compared to the CA2 virgin aggregates. And even though section CP10 had higher wrap thickness compared to section 9, it failed early, which means the virgin aggregates capping in section 9 played a major role in stabilizing the weak subgrade. Even if you look at the trenching pictures, let me go back a few slides, you will understand that. This was supposed to be only 3 inches, whereas the wrap thickness was supposed to be only 9 inches. But if you look at this picture, you will see that instead of 3 inches, it ended up somewhere around 5 to 6 inches. So that contributed to the superior performance of what we believe right now. So that sums up the TRB presentation, whatever we presented in TRB. Now the research progress, we have already completed all the accelerated pavement testing on both construction platform as well as on the low volume roads with HMA surfacing. Also trenching on all the 10 sections was conducted to assess the actual layer thicknesses. Right now what we are doing is we have done some lightweight deflectometer tests with these additional geosensors. From those deflection basins, we are trying to correlate the nonlinear material performances using the ILIPAVE based models, and then when we have got those moduli values from that ILIPAVE, we are going to normalize the magnitude of rotting, basically again using ILIPAVE with respect to the load level that was applied during the accelerated pavement testing. So that sums up my presentation. Any questions? Any questions or any suggestions are welcome. Okay, right.
In your outline, you said you were going to touch upon quality, construction quality. What's your opinion on it? How do you feel about the construction quality if you were targeting 3 inches of capping material and you were seeing 5 to 6 in some of the sections? Was there a lot of variability from one section to another?
Yes, there were a lot of variability. There are two problems that are associated with the quality control aspect. One is the subgrade was very soft in some cases, like we were targeting CBR1. Basically, we created a swamp, and with that swamp, you cannot even drive a construction vehicle. With a, with the bucket of the backhoe, we basically compacted it by thumping actions. That's how we compacted it. So whenever you are dumping those large rocks on top of that soft subgrade, it's very hard to maintain that uniform level up. If the CBR subgrade strength was a little bit higher, then you would have better control over on top of that sections. Also another factor is that you need to remember that some of these sizes are 6 to 8 inches in size. So if it is penetrating through that soft subgrade, it's going to add another 6 inches of your aggregate cover thickness. So that also affects the construction quality, also on the top surface. So these are the things that were affected. But with the smaller stones like CA6 wrap or the CA auto materials, we should have done a better job. But unfortunately, that was not the case. because of the higher thicknesses, the wrap sections perform better.
Was saying is also certainly what he's talking about with the large rocks, especially thicker layers, is correct for CBR1, which are 2 cells. He talked about the CBR3 cell,
Yes.
Basically cell number 3, but even in that case, you saw whenever we're building, putting a layer on top of the wrap material, and this is still a 1-inch top size wrap, like a typical CA6 gradation wrap, even that was the case with the full scale, with the HMA, low volume pavements as sub-base layers. With the roller compaction on top of the wrap material, we always have some issues. And that's also now showing up just like the thickness you saw in that virgin capping, so much higher than what we expected. Same things we see now with the HMA. Instead of 4 inches, some of the HMA sections with wrap
As close to
sub-base
6 inches.
already apparently in the construction built much thicker. And now we're investigating the reason for that further. There are some issues from constructability with wrap actually in sub-base courses that we're going to be pointing out in the study. Hasan is right now analyzing the density of asphalt cores taken from those different sections in the HMA pavement section, the south side cells sections. And there are some issues with wrap for sure that you'll find out actually what's going on there. Compaction is not properly achieved. All right. Thank you very much. Thanks, Hasan. Do we have any questions from we have any? Okay, the second presentation is also on aggregate materials, but this time Quarry By-products. And this is project 125. I think so. Wentig and Vincent will be presenting that one. This presentation was made at BRB by actually the BRB chair. What is the session?
Welcome, everyone. Today, Vincent and I will present the topic Characterization and Stabilization of Quarry By-products for sustainable pavement applications. So we have been working on this project for over a year, and this is presented on the TRB meeting by the TRB chair, Sheila Chairs. This is the outline of our presentation. So I'll start with the introduction, followed by the industrial survey we collected among the Illinois aggregate producers, and some properties of the Quarry By-products from the literature. And then Vincent will take over of our laboratory assessments and the findings. To start with the introduction, this is the motivation of our project. So nearly 2.12 billion of the tons of the aggregates were produced in 2009. And I have some more recent data that in 2014, last year, the production is 2.17 billion tons of aggregate, contributing to $19.8 billion. So we have a lot of material products, and about 8% of these products of aggregate is waste fines, which is the Quarry By-products we study. And stockpiling and disposal of all these byproducts is a major issue for the aggregate industry. And regarding to the Illinois state, we have the new practices have moving to finer gradations, which means we'll have more waste fines because of the more crushing and screening. And also, we are going to utilize more recycled material, which will result in more fines. So we have the motivation of our research, and what about the applications in the world? The figure on top right is the number of countries that are conducting the research on use of these quarry byproducts. You can see it mainly is Europe and the United States. And the more focus of the applications of these quarry byproducts are concrete, which is this one, and geotechnical applications. So what about in the US? In the US, this is the map showing the applications of these quarry byproducts. We can see that they are mainly in the eastern side of the country, and pretty much none of the applications are shown in the western side. And also, the most applications that are collected are hot mix asphalt and surface treatment, with only 5 applications for embankments, which is the subgrade. So we're more interested to see what kind of applications or what kind of potential applications these products may have for the subgrade. So quarry byproducts. By saying quarry byproducts, we are saying the materials less than 1/4 of an inch in size. They're mainly coarse and to medium to fine sand particles with some of clay and silt fraction. And they are produced in multi-processes in the quarry production, from blasting to primary, secondary, and tertiary crushing. These are some typical characteristics for the quarry byproducts from the literature. So from literature, we can see the gradations, particle shape, and some other physical properties, as well as moisture content, mineralogy, can be very important to these characteristics. And also, the literature shows that the untreated quarry byproducts have very low strength and resilient modulus. To start our research, we started with the industrial survey. So in 2013, we sent out the survey to 83 aggregate producers throughout Illinois. And we have respondents from 22 producers, which represents 42 quarries. Among all these respondents, there are 3 out of the 5 top crushed stone producers. They are more likely to have these access quarry byproducts problems. This is a map of locations of the quarries that responded. So you can see that it is almost all from the north to the south of Illinois. So we have some results from their survey. The typical annual tonnage of the quarry byproducts production. We can see over 55% reported they have greater than 100,000 tons of these quarry byproducts. And also 18% report that they have more than 100,000 tons that are in excess category. By this, we mean they are stockpiles, not being sold or used in any applications. And this is the current applications for the Illinois producers. We can see most of them say that they will sell their quarry byproducts as ag lime. Ag lime is one agriculture use, not in transportation use. And only 2.6% say they will use them as aggregate subgrade. So maybe there's a potential we can use them in this application. So we have 4 materials coming from the yellow stars locations. So we are pretty, we hope that they can represent the Illinois production. And in this paper, we only present the one in blue, which is near Chicago. So from a quarry near Chicago, we have 2 batches of materials. And for each batch of material, we have them from 3 crushing stages, from primary crushing stage, secondary crushing stage, and tertiary crushing stage. So for the 2 batches, we want to see the variability in sampling. And from the 3 crushing stages, we want to see the variability in crushing stages. This is a more close look at these products. This is the products from primary crushing. can see they are more like sand instead of fines. And they are more rounded. This is the material from secondary stage. They are more flat, and they are more sub-angular. Tertiary is little closer to the secondary in visualization. So after this, we started our laboratory characterization. So first with the chemical composition, followed by the grain size distribution and Aberg limits, so that we can classify these soils. And then followed by the particle shape using the imaging machine in HO, and then the moisture density curve, so that we can know the maximum density and the optimum moisture content. And then followed by the shear stress and compressive stress testing. This is the chemical composition of our material. We can see for the 3 different crushing stages, they are pretty much similar. They are from the one source that is reasonable. And they are, because this is the most important composition of this material, so they are from dolomite type of the rock. So we can see these materials can be soluble in acids, which means they may have low resistance to the mechanical and chemical weathering. So Vincent will take over the other half.
Okay, thank you, Wentig, for going overview of the project. I'm going to go through the lab characterization of Quarry By-products. As you see, we started off with Sieve Analysis, and the purpose for Sieve Analysis and other tests we did, like Wentig have said already, is just to understand the possible difference between these 3 types of materials and find how we can improve them. We also took a look into 2 batches, as Wentig mentioned, just to understand the possible difference that might come when you sample different samples at different time. So as you can see on the gradation, there's no big difference actually for all the 3 samples, all the 3 Quarry By-products we obtained, primary, secondary, and tertiary. The trend is pretty much the same, which is what you are more interested into. But if you take a look at the percentage passing number 200, it looks like tertiary had highest percentage passing number 200 compared to primary and secondary. Going up to the second batch, we also find the same trend in terms of gradation, but this time the percentage passing number 200 was a little different. As you can see, this time primary showed higher percentage passing number 200, and this was different from the first batch we collected in 2013. So we went to the modified methane brew, which is a test to characterize these byproducts in terms of clay content composition. We used modified methane brew, which has the most important tool for this one is the calorimeter, which you can see there, and the methane brew, which is a liquid. We mix it with the Quarry By-products, and then we shake. We take it back to the calorimeter, and then we get the values of the clay content for those materials. So as expected, we found out that primary had highest clay content, followed by secondary and tertiary. But generally, the clay content for these materials is not very high. We were expecting primary to have slightly higher clay content because during blasting and extraction of the rock, it's exposed to soil and other deteriorated materials, which might be having clay content from the Earth's surface. But after primary crushing, you are basically removing all those materials, and then you are having fresh rock, which is why we think the clay content reduced as you go from primary to tertiary. So at the bag limits, we also conducted at the bag limits as a general test for soils, and we found out that it was around 14 to 13, and all these Quarry By-products are basically non-plastic in nature. We were able to find this information also and match it with the literature review. So the soil classification, the sample classification of Quarry By-products, as we said, we did it for 2 batches, the first batch and the second batch. For the first batch, generally the Quarry By-products were characterized as 30% from well-graded to poor-graded. But for batch 2, it was well-graded since sand, and there were no difference in primary, secondary, and tertiary. To understand more about the gradation again and the difference that might exist between primary from batch 1, primary from batch 2, we used fineness mortars, which we calculated for both samples. So we were able to find out that for secondary and tertiary, there is no big difference. That's secondary batch 1, secondary batch 2, comparing the two. The same applies to tertiary, but for primary, there was slight difference compared to secondary and tertiary. So we also just conducted image analysis to understand the particle shape and size of these byproducts. Our focus was on angularity and F and E ratio. From what we saw for secondary and tertiary, there is no big difference between secondary and tertiary, but primary showed some slight difference compared to secondary and tertiary. So now we started characterization of these materials. We started moisture density test, which is a typical test done for soils. What we found out that the maximum dry density just decreased as you move from primary, secondary, and tertiary, with optimal moisture content between 10.4 and 8.6. Then we went to direct shear testing to understand the shear properties of these byproducts. We understand the vertical shapes might be different, and this might create some differences in the shear properties. So I wanted to take a look at it before we go further. What we found out that during the testing, there were actually no big difference recognized. The only surprising thing was friction angle, which was really high for these materials. This was probably attributed to the compaction we did before when we were preparing the samples. We compacted the samples to 95% of the maximum dry density, and we think this might be one of the reasons we have high friction angles. In terms of shear testing, also extracted some information just to see any difference that exists in the primary, secondary, and tertiary byproducts. In terms of load shear displacement, all the curves behave pretty much similar. For dilation values of these, the range were between 0.03 to 0.04 for both of the Quarry By-products. So, and then we did UCS testing. This is strength testing to see, are these materials ready to go out in the field and perform well? What we found out that the primary, secondary, and tertiary all showed very small UCS values. And these values are close to CBR of 2, with tertiary actually having CBR of less than 1. So all these strengths were really very small, and we decided to use some stabilization to improve the properties of these byproducts before we tried them out in the field. So we tried 2% cement, 5% sieve fly ash, and 10% sieve fly ash. We are emphasizing not only on cement, but also glass sieve fly ash. Basically, glass sieve fly ash is a byproduct on its own. So using a byproduct to stabilize another byproduct, that would be a plus if it works well. So we started off with characterization of the stabilized quarry fines. That's the moisture density testing with cement and fly ash. The only thing I want to mention here is the addition of cement raised the maximum dry density compared to the virgin material and then reduced the optimum moisture content. While the addition of fly ash slightly raised the density, but the optimum moisture content increased. So after doing all the density characterization of treated Quarry By-products, that's Quarry By-products with addition of cement or fly ash. We started testing of the strength of the samples. We cured the samples for 7 days at room temperature under 100% humidity, and we soak the materials 4 hours before we test them, just to get clear understanding of their behavior in wet conditions. So here are the values we found out. As you can see, the virgin materials is around 10, with tertiary having around 4 psi. But after addition of cement, the values raised to about 200 psi for both secondary, primary, and tertiary. The addition of 5% cement slightly reduced the values from addition of 2% cement. And our purpose was to see how much of fly ash can we use, at least to get the same strength of 2% cement. So we decided to raise the 10% to 10% class C fly ash, and the results were around 300, which is basically around 30 times increase from the virgin strength of the sample. So both 2% cement and 10% fly ash were really promising. So here is the summary of the finding. QB samples obtained are domatic type, as Wentig discussed already. These samples are non-plastic, as we have already just discussed. The classification of the Quarry By-product is solid and sand-sized particles. Primary QB samples were more rounded and cubical in shape. This can only be seen in the just physical observation, but also using image analysis, we're able to see that primary samples were different from other two samples. QB samples have maximum dry densities in range of 130 to 140 and optimal moisture content of 7 to 10.5%. Very low UCS of the virgin QB materials were observed, and then the addition of fly ash were able to raise the strength up to 30 times, which is really promising. So what are the potential utilization from the testing? Improving the strength of the Quarry By-products. What we suggest these materials can be used for further testing or verification. So we suggest subgrade embankment as one of the potential application. We also suggest leveling HMA binder. This one haven't looked much into it. I just checked the gradation band. I found out that addition of other aggregates with Quarry By-products can produce aggregate gradation band within the Illinois specified leveling HMA binder. So further than that, you haven't done much about this one. Also, stabilized base using these by-products for as stabilization for inverted pavements, which is where you have subgrade and then you have cement or fly ash treated soils, and then you have the base course on the top of it. This is, I think, is not really common. It just started recently. I read some articles about it from China. And then filling voids. Some of the research that was conducted by Professor Lilo from Texas, I found out that addition of or having 20% fines within the base course might still, the base course might still perform well if you just add 20% of fines. So we suggest to look into this one. The addition of these by-products might just close up the voids between the larger particles of the aggregate within the base course, and this might lead to performance of these materials while consuming some of the aggregate by-products. So our future work is to go deep into the green applications and do field testing just to validate the laboratory findings and evaluate the field performance of these materials. So this is all I have today. If you guys have questions.
your future effort on the green and sustainability, will that look into the either cost savings or increase by having to stabilize versus just using the material itself? Material versus one of these materials that's stabilized?
We haven't looked into this one
Future?
because I think this is still early. We still need to validate the application of these materials in the field and see if they are really working in the field before we go into that. But as part of this project is also finding the environmental benefits using life cycle assessment and of course the cost savings associated with application of these materials.
Yeah, the answer is yes, actually. Phase 2, all these options we're going to be trying out. And the phase 2 will be a field validation study which got approved by IDOT now. Hopefully we'll be approving it finally. Questions? Comments? Yeah, the interesting thing is that the aggregate subgrade use of filling the voids in the aggregate subgrade structure, there's a lot of voids we told, and I think that's what, again, the IDOT sponsor of the project is interested very much, to maybe combine the large stones, 6 to 8 inch, what the sun presented, and having these stockpiles, huge mountains of fines, in order to, with that purpose, now maybe with the large stones, which is again another win-win in my opinion, because you already want to make use of these plus by less crushing with larger sizes. Now you can actually build pavement foundations in a sustainable way. That's the direction.
Okay, thank you for your attention.
Thank you.